We begin again with Asilata Bapat, whose title is A Sphere of Spherical Objects.
Hello. Thank you, Rui, and thank you very much to the organizers for inviting me. It's great to be here. It's my first time at the ICTS. So I will talk about a sphere of spherical objects. So I'll explain all the words in the title. And this is three different projects, but I'll mainly speak about the first two. So the first is joint with Anand Devpurkar and Tony Licata, and the second one is with Vincent Pilot. And then we have another project in progress with all of these people, which is more combinatorial anyway, so I won't discuss it much. But let me just start with some motivation, because I get the feeling that this talk is slightly different from the themes of this conference, so I'll try to give some motivation and some intuition of why we want to study this problem. So the motivation that we have, is that we want to study the topology of the space of Bridgeland stability conditions. And I'll say a bit about what that is, but this question is maybe not that interesting from some points of view, because the conjecture is that this space is always contractible if it's connected. So maybe that's not so interesting, but I'll say why I'm interested. And so we are going to work with some basic ingredients, which I'll list here. Just so that I don't have to keep listing them again. And this will be constant throughout my talk, more or less. So we will be interested in two Calabi-Yau triangulated categories. Okay, so these are categories P, which have a symmetry property in their morphisms. So if you take the morphisms between two objects, that's the same as swapping them up to some shift, and there's some dual, let's ignore that. But basically the morphisms have a duality. And so it's sort of like in algebraic geometry, the derived category of sheaves on a K3 surface would be an example of this. And the second ingredient that we're interested in is spherical objects, which came up in the title. So these, for me, are objects X such that of the category. If you take the endomorphism algebra of this object, it looks the same as the cohomology algebra of the two sphere. So that's these are the objects that I'm interested in. And I'll just say a quick word about why these are interesting for me. It's because these are the sort of simplest possible objects in terms of endomorphisms in a Calabi-Yau category. So this is the smallest possible endomorphism ring you can have. And I will let boldface S be the set of spherical objects. In C, and I'll usually take them up to triangulated shift. And the last main ingredient that I have is that these categories C will often carry a group action, namely the action of some sort of braid group. So these are not necessary, so you can ask questions. All the questions can be asked without these restrictions, but the answers are very nice if you impose these restrictions. And I'll say one thing about this talk. All of the technical stuff is in the beginning of the talk, and the talk gets extremely elementary towards the end. So if you don't like the stuff, you can come back in a few minutes. Okay, so of course, I'm interested in Bridgeland stability conditions on my category C. So let me give a pseudo definition. I won't give the full definition, but a Bridgeland stability condition on C is a certain collection of choices on C which satisfy some compatibilities. Okay, so it's specified by, so the first thing is the heart of a bounded T structure. Some sort of subcategory, abelian subcategory of C. And the second is a stability function, or central charge if you want. And typically this is written as Z, which goes from the Grothendieck group of this heart into the complex numbers. Okay, and I'm just going to get all the technicalities out of the way, and then I'll say more things. And the other thing, the restriction that this needs to satisfy is that all the objects of the heart themselves must map to the upper half plane. And with this setup, you get some sort of notion of stable and semi-stable objects, which is very similar to slope stability, for example. So in this, under this setup, we say that X in the heart is semi-stable if, now this definition is probably familiar. For all sub-objects in the heart, we have non-zero sub-objects. We have that the angle, the argument of the sub-object is strictly, or non-strict, I guess, less than the argument of X. So if the inequality is non-strict, it's semi-stable. If it's strict, it's stable. This is very similar to the slope stability definition. So that's very analogous. But let me just say one thing. So I've given you this particular definition, but the beauty of Bridgeland stability conditions is that there's another definition which does not preference a T structure, which is much more flexible when you actually want to work with these things. And so even though there's some abelian category which has appeared now and will appear later on, we will soon move out of that. So, so you have to be prepared to move out of the abelian world. And that's actually a good thing because, okay, so I'll say that in a minute. And then the last thing I need here, the technical thing that I need is the notion of a Hardan-Narasimhan filtration. So I should say, you need all this data which is subject to some conditions. So every object X in the heart has a unique Hardan-Narasimhan filtration. So something like this, and again, I'm stating this only for the abelian objects, but secretly the same notions hold for all objects, okay? Such that the subquotients here, so you have one, and so you have, the argument of A1 should be strictly bigger than the argument of A2, and so on. Again, this will be familiar if you work with slope stability. Okay, so I want to make one remark here. So often when in algebraic geometry we look at Bridgeland stability conditions, we're interested in the moduli of stable objects or something like this. And that's actually absolutely not the point of view that I want to take here. In fact, in this talk, I'm very much interested in objects that are not stable and objects that have Hardan-Narasimhan filtrations, because what we want to do is we want to vary the stability condition and see what happens to their filtrations as the stability condition changes. Okay, so it's kind of a totally different, somehow orthogonal point of view in some sense, but that's what we're doing. And so to do this, let me also state the famous theorem of Bridgeland. And the theorem is that the set of all stability conditions, like this, has a topological structure. And so I'll say the space of all such stability conditions is a complex manifold. And for this talk, I'm only interested in the topology, not necessarily not the complex structure. And the conjecture is that this space, which I'll call stab of C, is pretty much widely believed to be contractible. If it's, or let's say the connected component of some. Okay, so this is kind of the big conjecture. And then you might ask questions like, okay, if it's contractible, is it a ball? And we did some prior work which kind of indicates that in some cases it is a ball. And then you might ask, what about its boundary? You know, if you compactify this thing, do you get some nice boundary? And so this leads us to a sphere on the boundary. And this is more than just an analogy. So, you know, this makes it sound like some speculation, but actually in a theorem from a few years ago, we showed that the spherical objects, in pretty wide generality actually, the spherical objects can be realized as limit points of stability conditions. So I'm not stating this precisely because I don't need it for the rest of the talk, but this is still motivation. So this is the motivation of why we want to study sphericals, and somehow now we kind of change our point of view and say, okay, forget about this space of stability conditions. Let's just look at the spherical objects and see if there's some sphere that they sit on, like some natural topology. Okay, so that's the kind of punchline of the motivation. Yes? So I'll say it without writing it down because I don't want to go into it. But in a prior theorem, we proposed a compactification of this space of stability conditions by embedding it. It's some kind of analog of the Thurston compactification from Teichmüller theory. I don't know what that is, but yeah, there's some embedding into some big space, and then you take the closure there, and then you can figure out what the limit points are. And so there is some particular way in which spherical objects sit in the boundary.
That is with a spherical object?
No, it's a limit. So a limit of stability conditions. It's a limit point of stability conditions under this embedding. But we can chat later. But this is somehow that's all I want to say at the moment about.
So maybe can I so is the idea that the central charge of a given spherical object goes to 0 at that?
That's right. So yeah, certain things go to 0 which are not allowed. Maybe the central charge or the magnitude. Yeah, exactly. And so there are other proposals for these kinds of compactifications, but basically, yeah, these are not stability conditions for this reason, but they appear in the limit. But that's kind of the motivation. So find intrinsically, find a sphere on which the sphericals live. Okay, so that's kind of, this was sort of the vague portion of the talk. And now we come to the actual objects. And there's a little bit more technicalities, but then there's a very beautiful answer at the end. So please come back if you fall asleep. Okay, so now let's look at the particular category that we want. So this, again, the question can be asked completely generally. There's no restriction.
Okay, so,
Yeah.
So you want the spherical objects to be unstable.
In general, they will be unstable, yeah. There are many, many spherical objects, so you can't expect most of them are unstable. Okay. So, right. So the category C that we are interested in will be a category coming from some sort of representation theory. So this is, I'll call it the Tu Calabi-Yau or maybe the Khovanov-Seidel category. of the AN Dinkin diagram. So again, I'll give a brief overview of what I want here. So let's recall the AN Dinkin diagram. N vertices connected in a line. And there's a root system associated to this setup. Okay, and it has simple roots, standard simple roots, alpha 1 through alpha n. And on this root system or the root lattice, there's an action of the symmetric group, which acts by reflections Si, which is typically like the transposition I plus 1. Okay, so the category that we're interested in is going to be a categorification of this standard representation of the symmetric group. So it's a category, which I won't again define for time reasons, but I will tell you its main properties. So this is a category which contains a particular heart with simple objects which we write as P1 through Pn. And it carries an action of not the symmetric group, but the n+1 strand braid group. I'll write sigma I, okay? And these sigma I, so if you recall, these generators of the braid group, they do not square to the identity, but they braid. So if there are sigma I and sigma j that are far away, they commute, and if they're close by, then they braid. Sigma I plus 1, so I'll just write that braid relation. So recall, so there's a relation in the braid group. Okay, and okay, so it's generated by n of these sigma i's subject to these relations. And the symmetric group is a quotient of the braid group by adding the extra relation that the generator square to 1. So, so this is an upgrade of the standard representation on the root system. And to go back from here to there, you take the Grothendieck group. So that's the category that I want. And moreover, I should also tell you what this action is. So the generator sigma I acts by what's called the spherical twist, the Seidel-Thomas spherical twist. In PI. So the fact is that these PIs are sphericals. And there's an explicit formula for this spherical twist, which I'll write down just for completeness reasons. Let me start by writing the formula for the reflection. So SI acting on some arbitrary alpha is alpha minus alpha alpha I alpha I. And the formula for the spherical twist here is sigma I acting on some arbitrary x is the cone of, now I have to get this right, let's see. So some kind of complex like this. So it's the output of this will in general be a complex, even if you plug in something that was in the heart. So that's just for completeness. So the point is that these actions are completely computable by hand. So this is the category that I want. And now if you don't like this, that's fine, because there's actually a much more explicit model of the spherical objects in this category, which we actually use when we work with them. So I will explain that and then switch over to kind of that point of view. It's not a, it's not a two category. The 2 is for 2 Calabi-Yau. Like the symmetry has degree 2 rather than degree n. Sorry. Yeah, that's right. Okay. So what we want to do now is switch over to something extremely explicit. And the reason, I mean, we were attracted to this problem because, well, the questions can be asked completely generally. In this specific situation, there's a beautiful answer which doesn't use any category machinery somehow, as it turns out. So that's kind of intriguing. Okay. So let me explain this Khovanov-Seidel geometric model for the spherical objects. Of Cn. So I'll start with, the results of Khovanov and Seidel, and then I'll at some point explain there's a dictionary between some kind of topological thing and the categories, but we have some enhancements. So that will be part of the theorem. Okay. Okay, so we have and the inspiration for them when they constructed this was some sort of Fukaya category, but that's not my domain of expertise, so I won't try to say anything more about that. So the categorical objects that we start with, we're interested in the spherical objects. The basic ones are the PIs. Okay? And the idea here is that the n+1 strand braid group is acting on our category. And the n+1 strand braid group has a realization as some kind of mapping class group or pi1 of some topological object. And so that's what is used here. So to get a geometric thing of model of P1, what you do is you look at a configuration of points. And I'm going to draw them vertically for aesthetic reasons, because it'll be better when I talk about stability conditions to draw them this way. So I want to now look at a configuration of n+1 points. And if I look at the ith and i+1st point, then I look at this straight line segment joining them. So the idea here is that objects here, spherical objects here, will be some sort of arcs on this configuration. And the braid group is pi1 of the unordered configuration space of n+1 points. Okay, so that's the connection. So of course now here you can act by braid twists, and you can also act by braid twists here, and the braid group action here is a half Dane twist in each of these little segments. Okay, so maybe I'll just say, so sigma j, or sigma I of x maybe. So pi corresponds to this segment, and sigma I, the operation, corresponds to the half Dane twist in this i+1 segment. Okay, so it's a local topological transformation. And so using just this information, we can now reconstruct, I mean, if you have another spherical object which is realized as some braid group element applied to some pi, you can then get it here. Okay, so more generally, spherical objects is, so what will be the output if you start with one of these and you start applying braids? You will get some kind of non-self-intersecting arc which starts at one point and ends at some other point. Okay, so with distinct endpoints. And so I'll draw an example. So let me just restrict myself to 4 points here. Okay, something like this. And it turns out, if you do the calculations, this is, for example, this can be realized as sigma 1 squared, sigma 3 squared of P2. Okay, so it's actually now very easy to do the computations here because you can just do them. On the other hand, there's also an explicit formula for the spherical twist. So you can also do the computations on the left-hand side and you can reconcile them. And in fact, there's also, what do I want to say? So there's a recipe for going backwards. So if there's a curve like this, which is non-self-intersecting with distinct endpoints, then one of the results of co-invariant Seidel is that you can take that curve and you can deduce the object from it. In particular, you can deduce its Jordan-Holder composition series, and you can reconstruct the object. So, so kind of you can go this way and deduce the Jordan-Holder factors and also the object itself up to some overall shift. Right, so in particular, you can figure out what the simple pieces are. And the recipe is actually quite elementary, so I'll explain how to go about it. It's you put the curve in kind of minimal intersection position and then count its intersection with kind of these horizontal lines, and each horizontal line corresponds to a PI, and that tells you how many PIs there are. And then, of course, you need some extra data about how they glue, and the gluing is kind of given by the, connections are morphisms. So that's how you reconstruct, and it's very beautiful. So you can do that. And so now that's great, but this is not the only configuration of n+1 points. And so you might ask, what happens if you change the configuration? Can you get some more information? And on the other hand, the Jordan-Holder filtration is not the only filtration that you have. You have all these Harder-Narasimhan filtrations as you change the stability conditions. And so our aim was to kind of reconcile these two things. Okay, and so, right, so the question is, what about HN filtrations on the categorical side, and on the geometric side, what about other configurations? Okay. And I'll say just one word. I mean, one of the main theorems of this paper of Cohen and Seidel was that using this geometric model, they were able to prove that the action of the braid group on this category is actually faithful. And so this geometric model for them was actually useful to prove some kind of faithfulness. So that's the theorem. But now, okay, so now in order to describe a Bridgeland stability condition or to get to Harder-Narasimhan filtrations on this category, what we need is really a central charge or stability function. So we need a stability function Z from the Grothendieck group of this heart to C. And the heart has n simples, and it's a finite length category. So the nice thing about this representation theoretic world is that every object has a finite length composition series. And so all we need to specify a homomorphism like that is to specify a complex number freely for each PI. Okay, so it's meant to be a homomorphism from the Grothendieck group to the complex numbers, an additive homomorphism. This heart is generated by the simples P1 through Pn, so you just specify a number for each PI, that's all you need. And so that all you need is really, you want to send PI to somewhere inside the upper half plane.
So are you also going to give a geometric model for the stability condition?
Yeah,
in terms of
getting to
form of
my, you're
differentials?
getting to my punchline. Yeah, that's right. Yeah, so we want to do that. That's right. So, right. And then actually, so, astute listeners will remember that there's some Harder-Narasimhan property that we need to satisfy. You can't just produce any numbers you like, you might say, but actually, for these finite length categories, the Harder-Narasimhan property is automatic. So we don't have to worry about it. As long as we give one complex number living in the upper half plane for each pi, we're done. And so then, by the way, since I'm restricting myself to a single heart, I will call these standard stability conditions. Or let's say a standard central charge stability function. So now, let's draw this. And the upper half plane, I mean, there's some matter of convention, but for us, it actually doesn't matter. So we kind of include the positive axis and don't include the negative axis. It's not so important. But now, for example, for 4 points, or the category A3, right, corresponding to A3, we have 3 complex numbers to choose. So we can do whatever we want. Something like this. Okay, so that's an example of a central charge function or stability function. And once you specify this, you've specified a Bridgeland stability condition with this heart, and then you can compute Harder-Narasimhan infiltrations, etc. So now it's actually very easy to translate this to a configuration. And all you do is you start at the bottommost point and start following P1, and then P2, and then P3. Okay, so I've arranged it so that I start at some arbitrary point. It doesn't matter. It's all up to translation. So you start at some arbitrary point, and you arrange the points so that the vector going from the bottommost point to the second point is exactly the vector associated to P1. The second and to third is like P2, and the third to the fourth is P3. Okay, so it's a very simple translation. So that's how you get to a configuration. And actually, maybe I'll redraw this slightly just for, to make it a bit easier to draw things. Something like this, which maybe doesn't quite match the picture, but it's okay. And now the idea is, okay, now this configuration is not the same as this, but it's obviously an easy deformation, right? So the curve that I had drawn here, I could also draw over here. I just, I take some simple deformation from this configuration to this one, and then redraw the curve. And so that curve starts here, goes up like this, and does that. Okay. So this was the object, sigma 1 squared, sigma 3 squared of P2. The object didn't change. The same object. I can draw it here. Okay, so this is still sigma 1 squared, sigma 3 squared of P2. And then, but the interesting thing here is that now, once you deform, so this configuration has all points collinear. And once you deform, kind of let's say you've removed all collinearities, so you have fewer, I don't know, you have, in some sense, you have more straight line segments. So you have, a segment which was P1 and kind of P2 and P3, but you also have this segment here going from the bottommost to the topmost point, which now doesn't cross any other point. And then you have this one here, and you have this one here. So these are obviously special with respect to this configuration. And now you can all guess the theorem, and I'm just going to write it. And so the point is that the straight line segments are exactly the objects that are stable. So I'll write it here. So for a chosen configuration, okay, which describes a standard stability condition. The stable objects, let's say, I'll call this stability condition tau. So the tau stable, indecomposable, let's say, or let's say spherical objects in C, up to shift, of course, correspond exactly to the straight line segments. Okay, so in this configuration, just to draw it here as an example, so these, how many are there? 6, are the 6 indecomposable spherical stable objects which correspond to this stability condition. And in general, if the points are not in general position, so no 3 are collinear, then the number of stable objects that one expects is exactly the number of roots in this root system. And so you can check that this is exactly corresponding to the roots. And now you can enhance this a little bit to account for points that are collinear as well. So let me just, this is not much of an enhancement, but let me just finish this train of thought, right? So for a chosen configuration, which describes a standard stability condition, the tau semi-stable sphericals up to shift are precisely what we call in the paper the pseudo-straight arcs. And what does this mean? I'll just draw it as an example. So essentially, if you have collinearities, then a pseudo-straight segment is one that goes from some point to some other point. It wants to be straight, but it can't because it goes through these points. So it just avoids. You can, I mean, it's an all of this is up to isotopy, so it's an equivalence class of these things which has minimal length. And so that's a pseudo-straight segment, and then you can have several pseudo-straight segments with the same sort of shape. Yeah.
This is a case where you have semi-stable, which is not polystable.
That's right. Semi-stable, yeah, which are not stable. Yeah, so if you have, so the generic situation is when everything is non-collinear. If you have collinearities, you can have semi-stable objects which are not stable, and these are exactly the ones. Yes, it's what is drawn in the picture. So they are almost straight, but they're not allowed to be straight because they would hit other points. And so they just swerve to avoid points. It's too long to write, I'm sorry. I don't Exactly, yeah. So, it's 2 to the some number of, you can compute how many. Okay, and it should come as no, I mean, of course, the PIs, right, the straight line segments joining successive points are always stable, and that should be no surprise because simple objects are always stable. So that's consistent. Okay, and now we come to the Harder-Narasimhan filtration. Okay, so now what about, so we described the stable or semi-stable objects. So what about the Harder-Narasimhan filtration? Okay, so let me just now, I'm going to switch just to drawing these pictures because it's quite transparent in this story. So if you now draw some, and a spherical object now is some complicated arc which starts at one point, ends at another point, doesn't pass through any other points or itself. And so it could be, going to struggle to draw this on the board somehow. I don't know. Something like this. And the idea is, so let me back up to this case again, where the points were all collinear, where there's no stability condition data in the picture here because this is just all collinear points. And it follows from the work of Khovanov and Seidel, although they didn't write it down in their paper, but it follows from their work that if you trace out the object that you get from this, and you compute its cohomology filtration, the pieces of the cohomology filtration can be also recovered pictorially. And they're just what you think they might be. Like, you're going along straight, almost straight, and then you make a U-turn, and you're going along and you make a U-turn. So if you cut along the U-turns, you get the pieces of the cohomology filtration. So that's a consequence of their work. And so the theorem that we have is very similar. So here again, you can imagine that this whole string is some kind of rubber band, and you snap it to the points, and you get some straight line segments. So I'll just draw the segments that you get if you snap this tight. Of course, you can decorate these segments by how many of them there are and things like this. But at the moment, let me just remember this. And so the theorem, actually, maybe I will decorate them. So this is 3, that's all. And so the theorem is that the Harder-Narasimhan factors of a spherical X, which is an arc, are precisely the kind of, let's say, pseudo-straight pieces obtained by cutting the arc of X along bends. And so the way I've written this theorem, it tells me that whatever this object X is that I've drawn here, it has, if you write down its Harder-Narasimhan factors and forget the shifts, I get 3 copies of this stable object, 1 copy of this stable object, 1 copy of this one, and 1 copy of this one. And if you do more work, you can also like reconstruct the gluing morphisms and so on. So you can of course reconstruct the whole object from this data, and that's kind of repackaging Khovanov and Seidel. So the reconstruction business is repackaging Khovanov and Seidel's story, but the theorem here is that actually you can visibly see the Harder-Narasimhan filtration just by this geometric model. And now, for the last part of the talk, I'll switch to kind of a little bit of combinatorics, because that's where the sphere will come from. And so let me just say, okay. So the starting point was a spherical object X, and the ending point was some kind of labeled graph like this. Yeah. Yeah, absolutely. Yeah, if you so varying the stability condition corresponds to deforming these points, and the arc moves along. So for example, if I moved this point and moved it to the other side, then these two would merge into a single table. Yeah, absolutely. And that's yeah, we want to study that's at least. So standard here just means that I've preferenced this particular abelian category inside. There's no need to preference this, it just makes things a bit easier, but yeah. Yeah, that's right. That's right. So you move, in practice, I mean, I often tend to think of it as like just moving the central charge, but then also lifting it to a path in the stability manifold. So you start by, the naive thing to do is to move the central charge, and then of course the heart moves along with it.
The term is actually that if you just deform the stability condition, you get all nearby stability conditions. That's the statement about being a complex manifold. So
the complex structure comes from the central charge anyway. So that's right. So the statement of the Hardy-Narasimhan filtration itself hasn't had an ordering. Yeah, that's very good question. That's an excellent question. It's I know the answer. I'll tell you the answer, but it's not a very easy answer. So the ordering comes from the following procedure. So you start at one end, and as you move along, you keep track of some kind of winding number, and the maximum winding number, the point at which you're sort of maximally wound, is the first factor. And the second, the next one, it's not visible from this picture. It's not apparent from this picture. It can be computed, but you sort of have to trace the whole thing. Yes.
The category CN. And is the category CN also the derived category of representations of preprojective algebra of quiver AN is the same?
I have to think about it. There's some, it's almost the same. There's some slight thing which I need to, yeah, what I work with is the zigzag algebra, which is causal dual somehow. But I don't know if I think not quite an equivalence, but it's almost an equivalence.
Okay, thanks.
Okay, so I'll just say, so right, so now we want to kind of move from this picture to this picture, and so every spherical object has an associated graph like this once you fix a stability condition, or once you fix a configuration. And so we want to organize the outputs that you get. And the outputs that you get, I mean, if you stare, this is not a very difficult thing to do, but if you stare at what happens if the possible outputs that you will get here will be graphs with certain properties. And the properties are that, like, in particular, you can't have crossing edges in these graphs. This is a constraint. And now I just want to frame it this way. I mean, there is a constraint on the types of Hardy-Narasimhan factors that can appear together in the HN filtration of a single spherical object. And that constraint is visible here, but it's sort of not apparent homologically. So that's one of the questions for future work. But like if you have an arc like this and you do this procedure, you cannot get crossing edges. So the output has no crossing edges. Output graph, let's say. And there's another property which is not, I mean, it's automatic for this particular configuration, but actually there's a local property that happens at every vertex. So at every vertex here, assuming that you're going around that vertex, you are going around that vertex. And so you can't have a tripod at any vertex. Okay? So no tripods. So things like this cannot happen. Okay? Stated differently, at every vertex, all the edges that emanate live in a single half space. Okay? So it turns out, if you study graphs with these properties, it turns out that people have worked on them for 20 years, 20 plus years in computer science and kind of combinatorics. And graphs that satisfy, maximal edges, sets of edges satisfying this property, these properties have a name, and these are called pointed pseudo-triangulations. So I'll draw some examples, but if the configuration of points is kind of convex, then these are just basically triangulations. There's also an extra constraint. You can't have all of the outside edges, but I'm sort of going to ignore that. So not all external edges appear, because the curve has to start somewhere and end somewhere. It can't go around the whole thing. Yeah, they're planar. Yeah, the original curve was planars. That's right. Right, so let me just draw some examples to give you a feel for what these things look like. So that's an example. maximal collections. I want maximal collections. So all of the external edges will always be there, and then you'll have some of the internal edges, but I'm not allowed this one. But for the same configuration, I can do, something else, and I can sort of do something else, and these are the only 3 possibilities for this particular configuration. You can also do the same kind of thing for degenerate configurations. So if you have a degenerate configuration like this, I'll draw just an example for, so this is an example. This is an example, and so on. So things like this. Right, and so what we study is we consider a simplicial complex on all possible pseudo-straight segments of a given configuration. And we say that the maximal simplices are these pointed pseudo-triangulations, which are abbreviated as PPTs. Okay, so finally, if you take any spherical object, then you can write down some subset of a PPT like this with some coordinates. So it gives you a point on this simplicial complex. And so spherical objects live on this simplicial complex. In fact, they live on the boundary of the simplicial complex because they also have this third condition. There are no external, there's at least one external edge that's missing. And so the fact or the observation is that the spherical objects live on the boundary of, let's call this simplicial complex sigma tau. So they live on the boundary of sigma. And so let me just, so we studied this simplicial complex, and we also studied what happens to it when you deform the point configuration. And we showed that when you deform the point configuration, whatever simplicial complex you have here, the one that you get after deformation is piecewise linearly homeomorphic to the one you started with. And so all of them are in fact PL homeomorphic to each other. And then if you go back, so by doing this process, you can go back to a convex configuration. And in the convex configuration, this is very well studied in cluster theory. And so it's known to be, a ball or sphere of the right dimension, et cetera. So what the theorem that you get out of this is that by studying deformations of stability conditions and how HN factors change, you get the topology of this simplicial complex. And the output is that this sigma tau is a ball of dimension 2n minus 2, and its boundary is a sphere of dimension 2n minus 3. And also, as tau varies to tau prime, so any path from tau to tau prime, we can, you can lift it to a PL homeomorphism sigma tau to sigma tau prime. And also, at the end of all of this, we started with a braid group action. So the braid group also acts on the sphericals. And the braid group acts also on the simplicial complex by PL homeomorphisms. Just by following this kind of the monodromy of this kind of thing. Okay, let me just see 3 more minutes. So now, so this was kind of the theorem. Let me just briefly mention the work that I did with Pilot. So with Pilot, we studied the combinatorics of this. And actually for points that are all aligned, so all collinear, just like the original Kohanov-Seidel story, we actually constructed a polytope out of this. So if this is now getting very far from the world of stability conditions, but if for the case of points in a convex arrangement, a similar construction would give the associahedron. And so this is a kind of collinear version of the associahedron, if you like. So that was a theorem with below, and in this joint work with all of these authors, we are now trying to construct a polytope for arbitrary configurations. So let me just mention that for generic configurations, without using stability conditions at all, there's a polytope that's constructed by Santos and his collaborators many years ago. But there isn't a unifying answer, and that's the work that we're doing with this group of people. And I'll end with mentioning some future questions, because all of this was a very specific example. And so what can you do in other cases, or what questions can you ask? So let me just okay, so this construction of sigma tau, of course, I stated it in terms of some point configurations and so on, but what you can do is you can take a stability condition in your favorite category and then construct a simplicial complex whose maximal simplices are the Hardan-Harriman supports of spherical objects, and then see what properties they have. So this makes sense in general, quite generally, I'll say, more generally. For other C. But there's a subtlety here. It makes sense when tau is a generic stability condition.
Your C is still Calabi-Yau 2 here, or no? Do you want C to be?
Well, I mean, you could define this whenever you want, but maybe it's better if it's actually 2 Calabi-Yau is better, because in 2 Calabi-Yau categories, if you have spherical objects, their Hn factors are also spherical when tau is generic. So that's what makes this stick. And so when tau is generic, the nicest place is for 2 Calabi-Yau categories. You can define this. But when tau is not generic, we run into issues, because what can happen is you can have semi-stable factors which are not spherical. So they don't fit neatly into the story, and so you want some kind of nice refinement, stable refinement of the Hn filtration. So some people in the room are experts on this story, so if you know anything about this, please let me know. So I mean, and in the type A story, we really needed to use the non-generic stability conditions. That's what made the theorem work, because you go from one generic stability condition to another by deforming and passing through a wall. So you need to understand the wall. So that's kind of the roadblock at the moment for more general situations. And then the other question, well, yeah, the other, I mean, kind of general question is, what are the homological constraints on Hardan-Harriman, supports, let's say, of, let's say, spherical objects in general? In type A, these constraints were explained by pointed pseudo-triangulations, but in general, experiments show that there are some constraints. Not all sphericals appear together, and there's some homological constraint here, which is a mystery at the moment. So these are kind of the questions, but the flavor is the same. Okay, I'll end here. Thank you.
So any questions?
So first a comment and then maybe a question. So to relate this to some of the other themes of the conference, so if you take this configuration of points and think of it as sitting in the cotangent fiber of the Riemann surface, and you let it move over the Riemann surface, you get a spectral curve.
Mm-hmm.
which is a point in the Hitchin base.
Mhm.
The simplest case would be 2 points, and you just have a rank 2, a quadratic differential. And then one can, ask all these questions about stability conditions
Sure.
in that context. So a spectral curve is supposed to give a stability condition.
Okay,
on
great. Thank you. Yeah.
chi-type category. So I was wondering, have you thought about, so then this relates, of course, to the Hitchin system and all of that. Have you thought about relativizing what you're doing over, so that would correspond to really compactifying the Hitchin base in that case?
So I have not thought about it, but I would love to chat about it. I mean, yeah, this is quite far from things I usually think about, but it's interesting, and this is why I'm happy to be here. So yeah, let's chat about that.
In fact, just for the audience, the picture on the poster was taken from the project of Carlos and Fabian and Ludmil, which is about this, related to the simplest case where the base Riemann surface is a disk, and the fiber is maybe one of these guys.
My question is very naive because I'm very ignorant of Bridgeland's stability condition. So as a general question, you were interested about the topology of the space of Bridgeland's stability conditions. I tend to think of that space as analogous to Teichmüller space. And there, the topology of Teichmüller space is not very interesting. But if you quotient by the mapping class group,
Yes.
then that is very interesting. Yes. And so here you can consider the group of automorphisms of the category.
Yeah, absolutely. Yeah, many people work on this.
That you can do in the example that you have been explaining here, considering the topology of that, not so much the
yeah, I mean, this is a big area of research actually, which I personally don't work on, but there's a lot of related work by Bridgeland and collaborators and other people.
But in your example, in this example
as well, I'll have to think about that a little bit, but it's something simple. Yeah. I mean, from triangle or something. Yeah.
Okay, thanks.
Okay. So earlier in the talk, you have mentioned type C and how it's contractible. So is it and that its boundary is conjectured? Yes. So do we know anything about the dimension of type C in terms of the generators of the braid group?
Yeah, I mean, in this for this particular example, yeah, you can compute it, and in particular for this example, it's this is the dimension. So yeah.
So in that theorem, when you vary from tau to tau prime, the proof is more interesting in the case when you cross a wall, or yes, when you stay in the chamber, it's sort of
nothing happens if you stay in the chamber. Yeah, as expected. So it only depends on the homotopy class type of the path, and
anything else? Other question?
So you start with an object which is described by some general curve, and then you get the Harder-Nussbaum filtration given by these straight lines. In the sort of metric picture, there's a dynamical process which takes you from a curve and straightens out the curve by a curve shortening flow.
Yeah.
So maybe here I think you probably didn't use that. Yeah, it was purely combinatorial.
That's right. Yeah.
But if you're doing more general categories, do you think that?
I think absolutely that will become relevant. Yeah. Yeah. I mean, yeah.
Okay, if there's nothing else, let's thank the speaker again. So we can start again in 10 minutes, so at 12:05.